Point 2 is implicit differentiation. So essentially we're just taking the derivative of more like with y's in the equation. It's not like something where y is by itself and we're just saying dy dx. So number 2, x cubed plus y cubed is equal to 18xy. So I'm taking the derivative of everything with respect to x. So when we do the x's, that stuff will be just like normal. Like when we take, like of x cubed, it's going to be 3x squared. When we get to the y part, though, or like on the right side, we have product rule, so that'll be a little bit. But like it'll be just like you would do with the x's. It'll be 3y squared, but then we have to multiply it by dy dx. Technically, I usually just write y prime for the ease of not having to write a ridiculous amount of stuff. So I've got 3x squared plus, we do the same way, so 3y squared, and then it's times y prime, or you can write dy dx if you're so inclined, is equal to, then I take the derivative of this over here, so this is a product rule. So the derivative of the first would just be 18, and then times y, plus the first times the derivative of the second, so that would be 18x times the derivative of y. Well, instead of it just completely going away like it does where it just becomes 1 in this situation, normally it's going to become y prime. So it would be 18x y prime for that part. So then the trick from there is I've got to get y prime by itself, ultimately. So you're going to end up with a final answer that has x's and y's in it on one side and then y primes all on the left. So I'm going to move the y primes to the left, everything else to the right. So I'm going to have 3y squared y prime minus 18xy prime is equal to 18y minus 3x squared. Then at this point, just factor out the y prime from the pieces. So I've got y prime times 3y squared minus 18x equals 18y minus 3x squared. Then I'm dividing, so I've got y prime is equal to, now I'm going to take out a 3 from the top when I do this, just so I don't have to write it in 2 steps. So I'm going to have 3 times 6y minus x squared inside the parentheses. And then on the bottom, when I'm dividing this 3y squared minus 18x, I'm going to do the same thing, take a 3 out of those. So then that leaves me with y squared minus 6x. And so then the 3's just cancel. So I end up with y prime is equal to 6y minus x squared over y squared minus 6x. And that would be your final answer. So sometimes on these, they'll give you an x and a y value to plug in to like find stuff too, but a lot of times you're just finding the derivative this way. 4. And this is, I think I kind of said this, but this is when you can't get y by yourself or y by itself. But if you can, obviously you should still do that, because then obviously you don't have to do implicit differentiation. Because in a sense, we're always doing implicit differentiation. It just doesn't, we don't call it that because like y is already by itself, but that's how we get the y prime. So this one is x squared is equal to x minus y over x plus y. So I see a quotient rule on the right. So we've got on on the left, 2x is equal to, over here we've got the derivative of the top, which is just going to be 1 minus y prime times the bottom, x plus y, minus the top, x minus y, times the derivative of the bottom, 1 plus y prime, all over x plus y squared. So now, one like this, it can be a little bit more difficult potentially to get y prime by itself. Obviously, it's going to take some more effort. The first thing I would do in a situation like this is I would probably go ahead and multiply and get rid of the denominator. So I'm just going to multiply it over here. So I'm going to end up with 2x times x plus y squared. And then over here, sometimes when you've taken a derivative, something's going to end up canceling out. But in this situation, I'm going to have to multiply first. So I'm essentially going to have to FOIL each of these respective things first. So I've got x plus y minus xy prime minus yy prime. And then I'm going to try to multiply this negative through everything here. So I'm going to have, or well, here, let's do this. I'm going to make this positive, make that negative, make that positive, and then I don't have to think about it as hard. So I'm going to have negative x minus xy prime plus y plus yy prime. Now at this point, that's obviously a lot of things end up canceling. So I've got an x canceling, x and negative x canceling. I've got a negative yy prime and a positive yy prime, so those are going away. Everything else looks like it has the same sign. So now over here on this side, I would have 2y minus 2xy prime, and then over here 2x times x plus y squared. And then from this point, I would subtract the 2y over. So 2x times x plus y squared minus 2y. And I'm going to go ahead now that I've done that to avoid having to write it again and divide by 2x, or negative 2x. So that's y prime. And then just if you can simplify it, you should simplify it. So then I can take a 2 out of everything. So since there's a 2 here, here, and here, I can do that. And so ultimately, y prime is equal to x times x plus y squared minus y over negative x. Another way I could write this, if I wanted to split this up into pieces with a common denominator, the x's would cancel on the first piece if I split this, so I would end up with negative x plus y squared and then plus y over x. So that would be another way that I could write it. Which way does the book write it? The book technically writes it this way, or they multiply everything through. I would take either of these, though. Either of those would be fine. Six. X equals the sine of y. Ideas on what I'm going to have to do with this one? So I'm obviously taking the derivative of everything with respect to x. So normally when we have just the sine of x, obviously that just becomes minus the cosine of x. Or, sorry, not minus, positive cosine of x. But in this case, because it's a y inside instead of an x, it's almost like I'm doing a chain rule. I basically am doing a chain rule. So this is going to over here just become 1, and then this is going to be the cosine of y, and then all times the derivative of the inside, which would just be y prime. So then I just divide by the cosine of y. So I have 1 over the cosine of y is equal to y prime, and cosine of y, or 1 over cosine would be secant, so this would be the secant of y is equal to y prime. So if you have a y inside of a trig function, or inside of obviously like a radical or anything like that, that's automatically going to become a chain rule, even though it's just like a single y by itself kind of thing. Do one more like this. 8. I've got x plus the sine of y is equal to x times y. So taking the derivative, I would have 1 plus, this is going to be the literally same thing that we had up here. So this would be the cosine of y times y prime is equal to, over here I've got a product rule, so the derivative of the first thing would be 1, so it'd just be 1 times y, plus the first times the derivative of the second, so that would be x times y prime. So I'm going to put my y prime terms on the left, everything else on the right, so I'm going to have the cosine of y prime, minus x y prime is equal to y minus 1. Take out the y prime, cosine of y minus x, and then just divide, so y prime is equal to y minus 1 over the cosine of y minus x. And probably not a shocker, the next stuff is that we're going to find dy dx and then find the slope of the curve at the indicated point. So we're going to be doing the same thing, but now they're, instead of just giving us an x value like they normally would that we're plugging in, they're going to give us an x and a y value, because obviously a lot of these end up with a y left in the derivative, so we'll have to plug in that value as well. And then we'll use that to find the slope. Obviously, when we get to finding the tangent and the normal, we'll be using the slope with the point to find the new line. But these ones right here just want us to find the slope. So 10 x squared plus y squared equals 9, and the point is 0, 3. So what would the derivative of this be?
2x plus 2y. Are we still like doing the y prime?
Yeah.
Okay. 2y, y prime, and then that's it.
Yeah, and it would be equal to 0. Okay. So then I just need to subtract the 2x and divide by 2y. You can do that all in one step. So y prime equals 2x, negative 2x, over 2y. 2's obviously cancel. So y prime is just negative x over y. And then you can obviously plug in your numbers now. So this would be equal to negative, and then we'd have 0 over 3, which is obviously just 0. So the slope of this line is just 0. Um, 12. X plus 2 all squared plus y plus 3 squared equals 25. So we've got 1 and negative 7. I guess they're all about the circles in this section. All right, so now I need to take the derivative of this. Now, they obviously have x's by themselves, and I still need to think about this as if it's a chain rule because I've got stuff inside, but a lot of it's gonna end up canceling, so I don't really have to worry about it. So I take the derivative of the outside, so that's gonna be 2 times x plus 2 times the derivative of the inside. Well, that's just 1, obviously. Plus, now this one's gonna be a little bit different. So I've got 2 times everything inside. But now when I take the derivative of what's inside, the derivative of y is y prime. So I'm going to have times a y prime out here is equal to 0. So then I'm going to subtract this over, divide by this. So I would get y prime is equal to negative 2 times x plus 2 all over 2 times y plus 3. Cancel out the 2's. So y prime is equal to negative x plus 2 over y plus 3. And then I can plug in the numbers now. So I would have negative and then negative 7 plus 2. Oh, nope, not negative 7. Numbers. 1 plus 2 over negative 7 plus 3. So I would end up with a negative 3 over negative 4, which is just 3/4. So that would be my slope. Find where the slope of the curve is defined. So these ones, essentially, we're taking the derivative and then we're figuring out what values of the function make it defined. So it'll make more sense when we get to an answer, but 14x equals the cosine of y. So what would the derivative of this be?
1 equals negative sine y times y prime.
Yep. So then I just need to divide by the negative sine of y. So 1 over the negative sine of y equals y prime. And so that would just be negative cosecant of y. So that's the derivative there. But I'm trying to find out where the slope is defined. So is there anywhere, this requires you to refresh a little bit on your trig graphs. Do you remember where cosecant has asymptotes? So cosecant goes with sine, so just as a quick little refresher here, we would have pi over 2 pi, 3 pi over 2, and 2 pi. So sine would look something like this. It starts at 0, goes up, down, down, up. Wait. Just 2 spots. Oh. There. So everywhere that sine crosses the axis, like at 0, there's an asymptote for cosecant. So any increment of pi, it would not be defined at, because cosecant would be up here like that. So that means that this is defined everywhere except where y equals k pi and k is an integer, because that accounts for anywhere positive and negative that would happen, that would be a problem. So on the trig ones, you kind of just have to know what their graphs look like, and just like, is there anywhere that it's going to cause a problem for it? So like sine and cosine wouldn't have an issue in and of themselves, but cosecant, secant, tangent, and cotangent all have asymptotes, so they would have issues with them. So you'd be finding basically just where are the asymptotes. But they don't always do this with trig functions. There's this can happen with regular functions too, and so we're essentially thinking domain, like what would cause an issue in our domain, and that's kind of how you're finding where the slope is defined. So 16 x squared plus 4xy plus 4y squared minus 3x is equal to 6. So we're first going to take the derivative of all of this, and then we'll find where it's defined for this one as well. So we would have 2x plus, I've got a product rule here, so the derivative of the first would just be 4 times the second y plus the first 4x times the derivative of the second, which would just be y prime. And then plus derivative of this part would become 8y y prime, and then minus 3 equals 0. And so we need to get y prime by itself, so I'm going to move everything over, and I'm going to go ahead and factor out a y prime from these two pieces here. So on this side, I would have y prime is equal to, or not y prime is equal to, y prime times 4x plus 8y equals, moving everything else over, negative 2x minus 4y plus 3. Then divide y prime is equal to negative 2x minus 4y plus 3 over 4x plus 8y. And then at this point, I'm looking for essentially anything that's going to cause a problem here, because now I have my derivative. So in general, when I have like a rational function, what causes a problem, if what's true?
Like negatives in the bottom.
0.
Something like
Yeah,
Yeah,
if the
yes.
bottom is 0. Yeah, if it was a radical, then a negative would be a problem also. So I don't really know if there's any that are going to end up being a radical, but if that were to happen, anything that makes the inside less than 0 would be a problem. You can have a 0 and a radical, but in the bottom we can't have 0. So essentially all I do for one like this is I'm going to take the bottom part and set this equal to 0. So 4x plus 8y equals 0, and then I'm just going to solve for y. So subtract 4x, I've got 8y is equal to negative 4x, divide by 8, so y equals negative 1/2 x. So the function is defined everywhere but here. Which is like kind of hard to like because pretty much any x value that produces a y value that's equal to that is going to be a problem. So essentially, negative half of any x value, if that's equal to y, it's going to be a problem because it's going to cause a 0 on the bottom. So that one's a little bit, I don't know. I feel like these problems are good, but they're not, I don't really think that's something you need to like worry that much about, to be completely honest. I don't think that they're going to give you a question like that and be like, where is this defined at? Like, but anyways. Let me look at what all we still have in this section. How do you feel about the implicit differentiation so far?
I feel like the hardest stuff was the stuff we started with.
Yeah.
But other than that, it's alright.
Yeah. I'm going to do, well, I don't really want to keep moving let's do this. Let's pause here, and then you can do the problems up to where we are to make sure you've got that before we move into the stuff with tangents and normals, because we've only got about 15 minutes left. And then we'll move into finding the tangent, the normal, finding the second derivative of implicit, because that can get to be, essentially you take the first derivative, you get y prime by itself. Then you take the derivative again, but if you still have y's on the right side, then you end up with another y prime. So then you have to take the function you found for y prime and plug it back in. So it's just a lot more, it's like a puzzle in a puzzle, kind of. Like it's not a chain rule, but it kind of feels like that, because like you find it and then you're like, oh, I got to plug that in. So if we're not confident with finding the first derivative, finding the second one's going to be a lot harder.
Yeah.
So, anyways. And then that's pretty much it after that. So we may not finish it tomorrow, but at least it'll get us rolling in that direction. So, problems.
What does, like, finding the derivative even do? Like, why would I find it?
There are things that it's, like, useful for. I mean, it mainly, like, I would say probably physics is honestly, like, the big one that they use it for. Now, things that you won't learn in this class, but, like, that if you continued to take calculus in the future, not so much what my dad does now, but what he used to do is, like, designing things and finding shapes and finding sections and, like, areas of things and stuff like that. He used a lot of calculus to do that with what he was doing. But a lot of computer software programming stuff now does a lot of that for you, so it's not as big of, like, a thing. But unless you're going really engineering field, like, you're probably not really going to use most of this. Or if you decide to become a math teacher, that's pretty much the only big scenarios where I would say you would use it. But, yeah, it just kind of... I'm sure there's other things, but, like, practically, not a whole lot.
Yeah.
So just a few, 1, 7, 9, and 13 up to this point. And then, obviously, if you want to practice some other ones, you can practice some other ones. But we'll jump in tomorrow with the tangent and the normals, and then just see how far we get in all that fun stuff. There's also some of just finding the derivative, but they're a little bit more of a complicated derivative of, like, with, like, radicals that cause a chain rule and all kinds of stuff in there.